Hello everyone and welcome back to the conclusion of Chapter 8. We're going to cover Section 8.3 and 8.4 in this video, and that will be the end of our initial introduction to hypothesis testing. We do hypothesis testing in Chapter 9, but it's a little bit different type of hypothesis testing. It's pretty similar, but it is a little bit different setup for it. So without further ado, in Section 8.3, we're going to be talking about the t-test for a mean. In Section 8.2, we did z-test for a mean. And remember that why we would do a t-test for a mean is when the sigma is unknown. Or in other words, we only know the s. And when we're doing a t-test, we only know the s, which leads to a t-test. Way to remember it is a t follows s. If you only have s, then you go to the next letter in the alphabet, which is t. And whenever you're doing a t-test, you're going to be using degrees of freedom. And so you're not going to go all the way to the bottom of the chart. You're going to use your degrees of freedom to know what level to stop on that table. So here's our familiar pattern. I know you're probably tired of this, but I'd rather you be tired of me than confused. So we're going to go through it a couple more times. So we have hypothesis test, just like with the confidence intervals. Are we doing a mean or are we doing a proportion? In this section, we're going to be still working on a mean. However, this time, is the sigma known or only the s? We're only going to know the s. And so because we only know the s, we're going to use a t-test because t always follows s. And this is what we did in Section 8.2. This is what we're doing here in Section 8.3. And then when we get to Section 8.4, we'll be doing proportions and we can go back to using the z-test. Okay, so the procedure for the t-test when we only know s is very, very similar to what we were doing with when we knew the sigma. The only difference is we still have the hypothesis and identify the claim, but we are always doing the claim on the alternative hypothesis. But first thing is hypothesis statement. Second thing is finding the critical value. Third thing is we're going to compute the t value rather than a z value. And we're going to be using degrees of freedom. N equals 1. This is actually off. We actually use the degrees of freedom in this step. But we're going to compute the t value using the formula for t value, which is this one down here. Okay, and we're going to make a decision to reject or not reject the null hypothesis, and then we're going to summarize the results. So we're going to find the critical value, but when we find the critical value, we're going to have to do degrees of freedom with that critical value. That's really the main difference, is that step 2 using that degrees of freedom. And so you'll see this formula is almost identical to what we were using before. It's just the z is now a t and the sigma is now an s. So let's see how we can determine the difference between the ones we were doing before and the ones we're doing now. So a study found hospitals in the state average 16.3 infections per week. Okay, so we already know, if you want to write it down, we already know our null hypothesis. A study found the state averages 16.3. So that's our null hypothesis, is that the average is 16.3. So we're doing means. A medical investigator wants to know if hospitals in their metro area are like the state. Okay, so they want to know if they're like the state. Haven't told us what we're doing quite yet as far as whether it's greater than or less than. I don't see anything greater than less than. Just wants to know if they're like the state. 10 hospitals sampled and a standard deviation. Is there enough evidence at a 5% significant to support that the metro hospitals differ? So there's verification that we're not talking about higher or lower. We're just talking about different. So the hypothesis statement is The null hypothesis is that the average is 16.3, and this researcher wants to know if their metro area is different than 16.3. Okay, so let's go to step 2. Now for step 2, we need to know what the tail is. Okay, we know it's a 2 tail. Hold on, let me write down what we're doing here before I do it. This is critical values. Or values, value or values. We need to know whether it's 1 tail or 2 tail. This is going to be 2 tail because it's not equals to. And that means we're interested in both directions, not just greater or less, but both. So it's 2 tail. Are we doing a z-test or a t-test? Well, let's look at what we have. 10 hospitals sampled have a mean of 17.7 infections and a standard deviation of 1.8. So right here it says 10 hospitals sampled have a standard deviation of 1.8. This is a sample standard deviation. This is an S. Our S is 1.8, not a sigma. So we're doing a t-test because we only have the S. Then we need to know our alpha level. Our alpha is 5%. And then the last thing we need to know for this, because we're doing a t-test, is we need to know our degrees of freedom before we go to the chart. So our degrees of freedom are going to be 10 hospitals is our N, minus 1, so our degrees of freedom is 9. Here's our little picture where we care about both tails because it's 2 tail. And so we're going to be getting an upper value and a lower value. And let's go to our chart. So we have a 2 tail test at, what was it? Alpha 0.05. But now we're not going to go all the way to the bottom. We're going to stop at our degrees of freedom. Our degrees of freedom was 9. And so we're going to stop at this level to get our t value. So alpha 0.05, 2 tails, meets up here at 2.262. And you can use whichever you would like. You can use 2.262 or you can just use 2.26. All right, so we have 2.262. For my exams or questions that I give you, it's never going to be close enough that whether you round to 2 or 3 decimal places will make a difference. So do what's comfortable to you. With all the Z's, we always go to 2 decimals. These slides go to 3 decimals, but it's fine. Okay, so we have 2.262 and negative 2.262. Then we're going to do our test value. And our test value is going to be t equals x bar minus mu over s over square root of n. So our x bar was the average that they got from the sample. And that was 17.7 infections per week. So 17.7 minus our mu that we used in our null hypothesis, which was 16.3. We're going to divide that by the sample standard deviation, which was 1.8. And we're going to divide that by the square root of 10, which was our n. So that would be 1.4 over whatever we get for the answer on the bottom. And 1.8 divided by the square root of 10. And then I'm going to do 1.4 divided by that answer and get 2.46. Then we're going to use that to compare. So where are we at? Well, 2.246 would be above 2.262. We would be in the shaded region, which is the rejection region. So what we're saying by that is 2.5, almost 2.5 standard deviations away from average, which would be fairly unexpected even from a sample. You expect a sample to not be right on the average, but this one is high enough above the average that it's unusual, and we're going to then reject the null hypothesis and support the claim that the hospitals in his area are different. Okay, so as we said, 2.46 is up here in the rejection region. Okay, and so we do reject the null hypothesis because the test value is in the critical region, and there is enough evidence to support the claim that the average for the hospitals in this researcher's metro area differ from the state average of 16.3 infections per week. So their claim is likely correct because we have evidence to support their claim. If this standard deviation was found to be closer to the mean, bigger than negative 2.262 or less than 2.262, in between those values in this white area, we would say, that's just because it's a sample, and a sample can vary. But this is far enough away with a standard deviation of 2.46 that we're like, that's pretty unusual, and so we will conclude that their claim must be correct. All right, let's look at this next one. Is a jogger's maximal volume oxygen uptake, it's kind of a long description there, but it's basically the largest amount that they can hold in their lungs, is it greater than the average of all adults? So basically, are joggers' lungs able to hold more oxygen than the average adult? And then it says the average adult is 36 milliliters per kilogram. So for our hypothesis statement, we have that the null hypothesis, the status quo, where we're at right now, is that the average should be 36.7. And our researcher thinks that a jogger's maximal volume oxygen uptake is greater than the average of all adults. So the mean is greater than 36.7 is their claim for these joggers. Step 2, for the critical values, we need to know the alpha. So in this case, the alpha is 0.05. 5% significance level. We need to know whether it's a t-test or a z-test. We know we're doing mean, but is it a z-test or a t-test? Suppose a sample of 15 random joggers has a mean of 40.6 and a standard deviation of 6. That was all referring to the sample. So this is a sample standard deviation of 6. That is an S. Let me bring this down here again. So S is 6. So since we only have an S, we're going to be doing a t-test. Let's stop right now and do our degrees of freedom. So our degrees of freedom from a sample of 15 joggers would be 15 minus 1 or 14. And then the last thing we need to know is if it's one tail or two tail, so that we can get to the right row on our table. And this is only greater than, so this is a right tail test. Only greater than is what we're interested in. So we're talking about right tail. So right tail t-test with degrees of freedom 14, alpha 0.05. See if we can locate that on the table. So one tail 0.05. Degrees of freedom was 14. We're going to come down, and we should have 1.761. Degrees of freedom 14, one tail because it's only right tail, 0.05 for the alpha, 1.761. Okay, so now we're ready for our test value. Test value is t, and it's x bar minus mu over sigma over square root of n. The sample average, the x bar, was 40.6. 40.6. The mu is what we used in the hypothesis statement. That's the 36.7. And then sigma, whoops, I wrote sigma. It should have been S. This should not be sigma. That should be S over n. And S was 6, and our square root of n was 15. Square root of 15. So the top would be 3.9, and then we'll do that over the answer that we get on the bottom. So we have 6 divided by square root of 15. Oh, we don't want that form. Let's do, I'm going to do F to D, which will get it to a decimal instead of A. This was like an exact answer, but it still had the square root sign in it. We didn't really want that. Probably doesn't matter the way we're doing it. I probably could have left that, but we'll just do that. So then we'll do 3.9. Oops, hold on. 3.9 divided by the answer, which gives us 2.52 approximately. Okay, so how does that compare? Well, that is in our rejection region. So 2.52 is up above our 1.76. And so, what does that mean? Think to yourself. If we're in the rejection region, then we're going to reject. And so there is enough evidence to support the claim. So, we are in the rejection region, and so we do reject the null hypothesis because the test value is in the critical region, in the rejection region. So the conclusion is that there is enough evidence to support the claim that joggers have a higher lung volume than the 36.7 mean of the population of adults. Do reject because it is in and there is enough evidence. And that's it for section 8.3, because this is so similar to what we did in 8.2. The only difference is recognizing that you only have the S, so you have to do a t-test and use that degrees of freedom. And the last thing we're going to do in chapter 8 rather, is we're going to look at hypothesis testing on a proportion. And as we know from the slide that I've shown you so many times, you probably want to scream at me. When we're looking at a test for proportions, we're going to go back to using the Z. Okay, so in section 8.4, this was 8.2, this was 8.3, and then in section 8.4, we're going to be back to using the Z test because we're doing proportion. All right. Now, how is the z-test for proportion different? Very little is different. The only major thing that's different is you have a different formula. Remember though, these formulas are all on your chart, on your formula sheet. You don't have to memorize any of these formulas. You just have to know what the variables are. If you go up to chapter 8 on your formula sheet, you can use this on your exam and you'll see z-test. There's the formula for z-test. Here's the formula for t-test. It even reminds you degrees of freedom is n-1, and then this is the formula that we're going to be using now. Z-test for proportions. Same thing when we were doing standard deviation. You have your z confidence interval, your t confidence interval, then you have your formula for if you're doing finding a sample size, and then you have your p confidence interval or your proportion confidence interval, and then your n if you're doing a sample size for proportions. So all the formulas are here. You don't have to memorize any of them. You just need to know which one to use and what the variables are. Okay, so back to our t-table and back to our problems at hand. Here's our t-table. So they say here on this slide, they remind us that a hypothesis test involving a proportion is actually a binomial experiment, or can kind of be thought of as a binomial experiment, where a success is finding something with the characteristic of interest, and then Q would be not finding something in your data set that was of the characteristic of interest. And what we need with the test for proportion is we need the sample size times the P and also the sample size times the Q, both to be at least 5. And that's because if that gets under 5, then lowering the number by 1 or raising the number by 1 that are in the have the characteristic of interest would change the proportion pretty quickly. And so they want to make sure that we at least have 5 when we take the n times the p and the n times the q. Don't really have to worry about that for our problems. We're just going to have problems where that's already taken care of, but do know that that is a requirement. So this is the test statistic for proportions. Again, it's a z. And we're going to be looking at the z row on the table. And we're going to be using p hat minus p over the square root of pq over n. Now, what is p hat? If you remember from before, p hat is just the number that you have in your sample that meet the desired criteria. So if you were looking at how many people said yes on a survey, it'd be how many people that said yes out of the total people that you surveyed. And that's how you get your p hat. And then q hat would be 1 minus that, but we don't use q hat in this formula. So we don't really need to worry about that. And then remember, p is the population proportion, and they're going to have to give us that. And then q is going to be 1 minus p. So let's look at a problem that uses the test for proportion. So this is what these types of problems will look like. A big hint when you're doing these kinds of problems that it's a proportion problem is you will see percentages instead of averages. So in this case, it says past research shows that 23% of Americans dream in black and white. They're not giving us an average, like an average number of nights they dream or something like that. they're saying what percentage meet this criteria. So 23% dream in black and white. So that's going to be the start of our hypothesis statement. Now, because we're talking about proportion, our null hypothesis is not mu equals, it's p equals. So our null hypothesis is that p equals 0.23. We could put 23%, but I think Alex always wants it in a decimal form, so we'll practice it doing it that way. But it would be perfectly appropriate to say p equals 23%. Okay, so the alternative hypothesis, let's read on. A researcher wonders if this average is different. Okay, so remember, different indicates to us that we aren't looking for a specific direction. We don't have a hypothesis about whether it's higher or lower. We're just curious if it's different. So the researcher wonders if this average is different for the elderly and selects a random sample of 100 elderly persons. Okay, so our P, seeing if it's not equal to 0.23 for the elderly persons that are in the study. Okay. They find that 28 of those in the study claim to dream in black and white. Is this enough evidence to support the claim at alpha equals 0.05? So let's see if we have all the info we need for our critical values. Now we're back to doing Z because all proportions are Z. So we know it's a Z-test because proportion is always Z. We have alpha equals 0.05. And then it's a not equals, so that means we're looking at both tails. And we're doing a two-tail test. So we're going to go to our chart, and we're going to look at two-tail 0.05. Okay, so two-tail 0.05, and we're doing a Z-test, so no degrees of freedom. We can go all the way to the bottom of the chart, to the Z row, and in the row that has all the Z's, we find 1.96. So that is our critical value that determines our critical regions, 1.96. Since it's two-tail, it's going to be negative 1.96 and positive 1.96. Step 3 is going to be our formula. Our formula is to get the Z, the test value, we're going to take P hat minus P. We're going to divide that by the square root. Again, I'm going to write this more appropriately. The PQ should be on top of the N, which equals our P hat. We don't actually have, technically. We kind of do because our sample is out of 100. But if it wasn't out of 100, we would have to compute. So our P hat is going to be 28 out of 100, but since percent means per 100, that's 28% or 0.28. Now, if it was numbers that weren't as clear as this, you would just take the top number divided by the bottom number. So 28 out of 100 would give us our P hat. So 0.28. Okay, and so that's our P hat. Our P is the same P that we used up here with our hypothesis statement, 0.23. And then on the bottom, be really cautious that you use the P in the Q, not the P hat in the Q. So the P, again, is 0.23. And then that would make our Q, let me write that down here. So Q is 1 minus 0.23, which would be 0.77. and then our n is the size of our sample, which is 100. So the top is going to be 0.05. I'll write that down because that's easy to compute. And then I'm going to do the bottom and divide that top by that bottom. All right, so we've got square root 0.23 times 0.77 divided by 100. And however your calculator handles it, make sure that all gets underneath the square root bar. So that gets us the 0.042, and we're going to take our top 0.05 and we're going to divide it by that answer. And we get 1.19 approximately. So that came out to be approximately 1.19 for our test value. How does that compare? If we look at 1.19 and we compare that to our critical region and critical values, it's in this area. It's before the 1.96, and so this is in the not reject region. We only reject if we're in the dark area. Like I said, think of it like you're walking along and you enter the cave. If you get into the cave, it's dark and spooky. We want to say no, reject, reject. But if you're out here in the clear, in the daylight, then you do not reject. So here's a nicer picture of that. So 1.19 would be to the left of 1.96. And so we do not reject the null hypothesis because it is not in the critical region. And thus there is not enough evidence to support the claim that the average number of elderly people who dream in black and white differs from the adult population of 23%. So, in other words, we would go on the assumption that elderly people dream in black and white at the same rate as the rest of the population. All right, and this is our last example for Chapter 8. And of course, it's another proportion problem. We know it's a proportion problem when we start seeing these percentages instead of seeing averages. So this one says, a report stated that 31.9% of babies are delivered by cesarean. A hospital believes that their cesarean rate is lower, and so they do a sample. So let's get our hypothesis statement. So our null hypothesis is the status quo of 31.9%. Remember, it's a P, so P equals 0.319. Our alternative hypothesis is that P is lower. They believe their cesarean rate is lower. So 0.319. And then for 2, for our critical values, we need to know the alpha, we need to know whether we're doing a z-test or a t-test, and we need to know whether or not it's a one-tail or a two-tail. So the alpha is 1%, 0.01. It is a z-test because proportions are always z-tests. It is a one-tail left, and I'll just say left tail, because we're only doing less than. So we draw our picture. We're only worried about this left-hand side. We're only worried about the less than side. And so we don't have to worry about the right side, only the left, so only one tail. So left tail, z-test, alpha 0.01 is what we're looking for on the chart. Okay, so we're going to go to this row, one tail, 0.01, and then we're going to do a z-test, and so we're going to go all the way to the bottom. And I'm sure some folks have got these z-scores memorized because we use the same 5, but I don't know. I don't know that I would recommend trying to memorize them and not look at the chart. I'd recommend looking at the chart each time just to make sure. So 2.33 is our z value, and it's going to be negative 2.33 because we are on the left side of 0. Okay, so we're now ready for our formula. Z will equal p hat minus p all over the square root of pq over n. In this case, we do not have the p hat again, so we'll need to calculate that. So p hat is how many in our sample met the criterion. So there was 13 cesarean out of 50. Again, some of you might be able to compute that in your head, but if you can't, don't worry about it. Just calculate it. 13 out of 50 would be the same as 26 out of 100. So that would be 0.26 for our P. So 0.26 for our P minus the null hypothesis proportion, the population proportion from the prior study, is 0.319. Then we're going to divide that by PQ. P, remember, is the second one, not the p hat. So 0.319. And then the Q would be 1 minus 0.319, which is 0.681. Okay, so we're going to take this times 0.681, and then we're going to divide that by the sample size, which in this case was 50. And then we're going to take that top number and divide it by the answer that we get on the bottom. So that top number comes out to be negative 0.059. Check that one on my calculator because I didn't want to mess that one up. And don't forget it's negative because we have a smaller number for our p hat than for our p, so it's going to end up being negative. And then we're going to divide that by whatever answer we get on the bottom. So we've got the square root, let me clear this up, there we go. The square root of 0.319 times 0.681 divided by 50. We have that answer, and so then we take negative 0.059 and divide that by that answer, and we get negative 0.895. Okay, so that's our test value. Where does that fall? Well, that falls very short of where we need to be. So 0.895 is going to be about in this area, which is not nearly as far down as we need to be for the negative 2.33. Kind of surprising. I mean, you feel like 6% away would be significant, but with proportions, you have to be quite a bit further off than 5 or 6% and or have really big sample sizes. And this wasn't necessarily a really big sample size. So we've got negative 0.895 here, not far enough down, still in the not reject region. This would be the rejection region, the shaded area. Okay, so we're not in this shaded area, which means we're in the not reject region. So we do not reject the null hypothesis because the test value is not in the critical region. And so there is not enough evidence to support the claim that the average number of cesarean births at their hospital is lower than the national or the reported average of 31.9%. So again, we took the null hypothesis to trial, charged it with being lower than 31.9%, did not provide enough evidence to support that, so we said he's not guilty. We're not going to reject the null hypothesis. We're going to say the null hypothesis is probably holds true for this hospital as it does for the other hospitals. So that's it for Chapter 8. And we will be back with Chapter 9, which is also hypothesis testing, but it's a little bit different hypothesis testing. Same general idea, but a little bit different setup. So good luck with your Chapter 8 homework, and I will see you back for the conclusion of hypothesis testing in Chapter 9.